Hello, myself Anibal Vishwas. Today I am going to explain the topic waveguides on the subject electromagnetic waves. Here are the contents that I am going to describe. Waveguides, basic features, what is rectangular waveguide, what is a circular waveguide, advantages, disadvantages, applications and conclusion. First, let's see a short introduction. At frequencies higher than 3 GHz, transmission of electromagnetic energy along the transmission lines and cables becomes difficult. This is due to the losses that occur both in the solid dielectric needed to support the conductor and in the conductors themselves. A metallic tube can be used to transmit a electromagnetic wave at the above frequencies. Let us see the basic definition of what is a waveguide. A hollow metallic tube of uniform cross-section for transmitting electromagnetic waves by successive reflections from the inner walls of the tube is called waveguides. As you can see here, these two are the waveguides. This is a rectangular waveguide, this is a circular waveguide, and from here wave propagation is happening. The basic features. The waveguides may be used to carry energy between pieces of equipment or over longer distances to carry transmitter power to an antenna or microwave signals from an antenna to a receiver. Waveguides are made from copper aluminum. These metals are extruded into long rectangular or circular pipes. An electromagnetic energy to be carried by a waveguide is injected into one end of the waveguide. The electric and magnetic fields associated with the signal bounce off the inside walls back and forth as it progresses down the waveguide. EM field configuration within the waveguide. In order to determine the EM field configuration within the waveguide, Maxwell's equation should be solved subject to appropriate boundary conditions at the walls of the guide. Such solutions give rise to a number of field configurations. Each configuration is known as mode. The following are the different modes possible in a waveguide system. The components of electric and magnetic field. Intensity is in EM. Here we can see the basic components of the diagram. In the y-axis EF, EY, HY, z-axis EZ, HZ, and in the x-axis EX, HX. Possible types of modes. Transverse electromagnetic, that is TEM wave, and transverse electric wave. Here, both electric and magnetic fields are directed components, that is Ez is equal to 0 and Hz is equal to 0. Transverse electric wave. Here, only the electric field is purely transverse to the direction of propagation, and the magnetic field is not purely transverse, that is Ez is equal to 0, but Hz not equal to 0. Transverse magnetic wave. Here, only magnetic field is transverse to the direction of propagation, and electric field is not purely transverse, that is Ez not equals to 0 but Hz is equal to 0. Hybrid wave. Here neither electric nor magnetic fields are purely transverse to the direction of propagation. Ez also not equals to 0, Hz also not equals to 0. Here we see the transverse electric mode and transverse magnetic mode. In transverse electric mode, the red lines indicate the magnetic flux and the blue lines indicate the electric flux line. Similarly, in TEM transverse magnetic mode, the red lines indicate the magnetic flux lines and blue line indicates the electric flux line. Uh, the magnetic flux lines appear as continuous loop, as you can see in both the diagram, and the electric flux lines appears with beginning and end points, as you can see in both terms with a similar structure. The wave propagation is happening in this direction. It is a rectangular waveguide. Any shape of cross-section of a waveguide can support electromagnetic waves, of which rectangular and circular waveguides have become more common. A waveguide having rectangular cross-section is known as rectangular waveguide. The dimension of a waveguide determines the operating frequency range. The size of a waveguide determines its operating frequency range. The frequency of operation is determined by the dimension A. This dimension is usually made equal to 1, half the wavelength at the lowest frequency of operation. This frequency is known as the waveguide cutoff frequency. At the cutoff frequency and below, the waveguide will not transmit energy. At frequencies above the cutoff frequency, the waveguide will propagate energy. Let us see the wave paths in a waveguide at various frequencies. At high frequency, the wave paths will be in disorder. At medium frequency, the wave paths will be in disorder with low angle of incidence and angle of reflection. At low frequency, the angle of incidence will be much shorter, and at cutoff frequency, like this, wave paths will be there. That is wave propagation. When a probe launches energy into the waveguide, the electromagnetic fields bounces off the sidewalls of the waveguide as shown in the diagram. As you can see in this diagram, the angles of incidence and angle reflection depend upon the operating frequency. At high frequencies, the angles are larger and therefore the path between the opposite walls is relatively long. As you can see in this one, the angle of incidence and angle of reflection are large, so they have a longer path. At lower frequency, the angle decreases and the path between sides shortens. Let us see in the see, at medium this has shortened in comparison to the first one at high frequency. When the operating frequency is reaches the cutoff frequency of the wavelet, the signal simply bounces back and forth directly between the sidewalls of the wavelet and has no forward motion. And at cutoff frequency and below, no energy will propagate. As you can see, at cutoff frequency there will be no energy propagation further. So what is cutoff frequency? The exact size of a waveguide is selected based on the desired operating frequency. The size of the waveguide is chosen so that its rectangular width is greater than one half the wavelength but less than the one wavelength at the operating frequency. This gives a cutoff frequency that is below the operating frequency, thereby ensuring that the signal will be propagated down the line. Representation of models. The general symbol for representation will be transverse electric M cross N or transverse magnetic M, where the subscript N indicates the number of half wave variations of the electric field intensity along the B dimension of the waveguide, and the second subscript N indicates the narrow of half wave variations of the electric field in the A dimension of the guide. The transverse electric 1,0 mode has the longest operating wavelength and is designated as the dominant mode. It is the mode for the lowest frequency that can be propagated in a waveguide. Let us see the expression for cutoff length. For a standard rectangular wavelength, the cutoff wavelength is given by this formula. Lambda is equal to 2 by whole root m by a square whole square by n by a whole square, where heavy are measured in centimeters. Let us see what is circular waveguide. A hollow metallic tube of uniform circular cross section for transmitting electromagnetic waves by successive reflections from the inner walls of the tube is called circular waveguide. The circular waveguide is used in many special applications in microwave techniques. It has the advantage of great power, handling capacity, and lower attenuation for a given cutoff wavelength. However, the disadvantage of somewhat greater size and weight. The polarization of the transmitted wave can be altered due to the minor regularities of the wall surface of the circular guide, whereas the rectangular waveguide, the polarization is fixed. Let us see the advantages of waveguides. Waveguides have several advantages over two-wire and coaxial transmission lines. Skin effect tends to increase the effective resistance of the conductor. Although energy transfer in coaxial cable is caused by electromagnetic field motion, the magnitude of the field is limited by the size of the current carrying area of the inner conductor. The small size of the center conductor is even further reduced by skin effect, and energy transmission by coaxial cable becomes less effective than by the waveguides. Some major disadvantages are: the physical size is the primary lower frequency limitation of waveguides. The width of the waveguide must be approximately a half wavelength with the frequency of the wave to be transmitted. Waveguides are difficult to install because of the rigid hollow pipe shape. Special couplings at the joints are required to assure proper operation. Costs are more and decrease the practicality of waveguide system at any other than microwave frequencies. Let us see some application of circular waveguide. rotating joints in radars to connect the horn antenna, feeding a parabolic reflector. TE01 mode suitable for long distance waveguide transmission above 10 GHz. Short and medium distance broadband communication to reduce attenuation loss can operate only above certain frequencies. Finally, the conclusion point. Electromagnetic waves can be guided along a desired route not only by transmission line but also by hollow pipes, dielectric coated surfaces, or dielectric rods. It is typical of all these hollow waveguides that one, they cannot support the TEM wave type but support the TEM wave types. And number two, they cannot transmit energy below a certain frequency known as the cutoff frequency. Waves of frequencies above the cutoff frequency propagate without attenuation. Waves of frequencies lower than the cutoff frequency, known as evanescence modes, are exponentially attenuated and do not propagate at all. Among hollow metallic waveguides, the most important are those of rectangular cross-section. There are an infinite number of both TEMN and TMMN modes that can propagate along such waveguides. Thank you.